Welcome back, everyone. Today we're going to be talking about nonlinear relationships. Now, if you recall, one of the assumptions of our general linear model is that all of the predictors influence the response variable in a linear way. But relationships in nature are often nonlinear. So how can we deal with these in the context of general linear models? Now, as I mentioned, general linear models assume that predictors influence the response in a linear way. And so luckily for us, there are ways in which we can take fundamentally nonlinear relationships from nature and linearize them through some form of transformation or other trick in order to be able to model them in our general linear model. So here I've represented a table of some of the common nonlinear relationships that we might encounter in nature. In each case, I've described the relationships in words, described the relationship in the differential form and the integrated form, as well as providing an example. The first row deals with our typical linear relationship that we might be used to, where we've got some response variable and we can predict that response variable by a linear effect of x, our predictor. In this case, in the differential form, the rate of change of y with respect to x is constant, and that's equal to our slope, or b. But the second example is an example of a fundamentally nonlinear relationship, like an exponential or a logarithmic relationship, where the rate of change of y with respect to x is not constant. Instead, the percent rate of change of y with respect to x is constant. Or another way of saying this is that the rate of change of y with respect to x is proportional to y. In this case, we have an exponential or a logarithmic relationship that we can linearize by taking the log transformation of our response variable. So when we do this, we can then model the percent rate of change of y by x in some linear way. So instead of trying to model y predicted by x, we're modeling the log of y predicted by x, which takes a fundamentally nonlinear relationship and linearizes it. So for example, we get an exponential decay in light intensity with depth in a lake, or population size might grow through time in an exponential way in an unlimited environment. And so we can use our general linear models in these cases that are fundamentally nonlinear by linearizing them and considering not the raw value of y, but the log of y as our response variable. Now, a second fundamentally nonlinear relationship that we can linearize using a transformation is a situation where the percent rate of change of y is related to the percent rate of change of x. And this corresponds to a power law relationship shown here, which we can linearize by taking both the log of our response variable as well as the log of our predictor variable. And in this case, then, we can take this power law relationship and represent it by a linear relationship that we can include as a general linear model, where the log of y is predicted by the log of x. Now, in addition to these transformations that can linearize relationships, sometimes biological patterns take on nonlinear relationships that don't follow any particular pattern. And what we can do in this case is to perform non-parametric analyses, which means that we're not going to fit a linear model to these relationships, but we're going to visualize them using some form of localized regression, either a cubic spline or what's called a low-S regression, which is just a localized regression, which is like we're fitting a whole bunch of tiny little regression lines across all of these different spans of the data, which allows our regression to not follow a linear relationship, but to follow this smoothed curve that's driven by the data points in a particular region of the overall scope of observations that we've made. Now, this isn't a way in which we can pull out parameters and make predictions, and that's why we call this a non-parametric analysis. It allows us to visualize the relationship, but we can't create any predicted values for a particular value of egg mass along the x-axis because we don't get parameters out of this relationship. The other thing to pay attention to is that this cubic spline that's performed in R using what's called a generalized additive model, when we fit a spline in R, this is very different than the spline that's fit in, say, Excel, where in Excel, you can control how wiggly the line is. In R, a spline is fitted using some objective criteria that try and make this line only as squiggly as it needs to be to adequately explain patterns in the data. Now, the other point to make about these splines in R is that they are localized regressions. And so you really do want to take with a grain of salt the wiggles that happen at the extent of your data. So you can see that through most of the data, the relationship that I've plotted here is mostly linear, but then we get this weird downward trend as we get to these extreme values. But this is potentially driven by the small number of observations that we have at very large egg masses. Now, normally those would contribute very little to the overall relationship in a linear regression. But in this case, we're talking about a localized regression. So when we fit a regression through these last 3 data points, they get pulled down quite dramatically. So the take-home message then is to not necessarily read too much into the wiggles in the relationship that happen during regions of our predictor variable for which we have very few data points. Now, as I mentioned, this sort of spline or loess approach to visualizing nonlinear relationships in R is helpful to see what the relationship looks like, but it doesn't really help us to be able to make any predictions because it's fundamentally non-parametric. We don't get parameters out of this relationship. So instead, what we can sometimes do is describe these wiggly relationships using either quadratic or polynomial terms, where instead of having a linear predictor of x, we also include a quadratic predictor of x squared, where we take our predictor variable x, multiply it by itself, and include that as an additional predictor. And what we get out of that is a quadratic equation that will describe a hump-shaped relationship, either a hump-shaped down or a hump-shaped facing up quadratic relationship. Now, in some cases, we use these quadratic or polynomial terms as a way of trying to describe nonlinear relationships in a parametric way. But in other instances, quadratic relationships have their own biological meaning. So in a selection analysis where we're trying to quantify natural selection using different measures of traits as predictors of relative fitness, we include a quadratic term as a way of trying to quantify either stabilizing or disruptive natural selection in a particular system. So how can we interpret these quadratic effects in our linear model? Well, we can do the exact same thing that we've always done. We're first going to write out our linear model where our response variable is equal to an intercept plus a slope multiplied by our predictor variable plus another slope corresponding to this quadratic term. Now, the way we interpret the quadratic term is by simply pausing to realize that x squared is simply x multiplied by itself. And so here we've expanded out our linear model, and we can calculate predicted values for a given value of x1 by just plugging in the parameters in our model here. But what I want you to realize is that when we expand out x squared into its components, meaning x times x again, I think what you can see is that this is exactly the same as our notation for a statistical interaction. So what this tells us, in the exact same interpretation as we had for a statistical interaction, is that when we have a quadratic term that represents a nonlinear relationship between x and y, what that's telling us is that the effect of x on y is not constant. It depends on the value of x. So let's slow this down a little bit. The effect of x on y is not constant, meaning the slope of this relationship is not constant. It depends on where we are along this x-axis. So we have a positive slope, but as we get farther and farther along this x-axis, this positive slope is becoming shallower and shallower and shallower. So as we get increasing values of x, this positive relationship is getting smaller and smaller and smaller. And you can see that from the parameters of our linear model that I've indicated above here. We have an intercept of 3. We have an effect of our x predictor of 23. But as we get increasing values of x, this slope of 23 starts to decline and decline and decline. And that's what's represented by our quadratic term. So we can represent nonlinear relationships using a quadratic term that will generate a hump-shaped relationship. And we can interpret this quadratic term in our linear model just like we did before, and even more specifically can interpret the quadratic part of this overall linear model as an interaction between x1 and itself, which tells us that the effect of x1 on y is not constant. It depends on the value of x1. Now, in other cases, the relationship between a predictor variable and a response variable does not change continuously across our values of x in a nonlinear way. Instead, we can see these abrupt changes in the relationship, where we might have no relationship below some threshold, and then a dramatic change in the relationship after that threshold, as I've shown in this figure here. Now we can represent this sort of breakpoint in a linear regression using general linear models, just like we've done before. The only trick is that instead of having a continuous predictor of the percent of matrix habitat, as we're predicting the woody species richness on the y-axis here, we need to create a new variable which tells our model whether we're in this zone down here below our threshold or this zone up here above our threshold. And the way we can do that in R is to use this nifty cut command, which creates a new variable, let's say called matrix 62, that takes our original x variable here and cuts it into categories that are either between 0 and 62.5 or between 62.5 and 100. So now we've created a new factor that says, is this predictor variable below 62 or above 62? And then we can include in our statistical model not just our predictor of the percent of matrix habitat, but also a statistical interaction with this new factor that codes observations as being either below this threshold or above this threshold. And importantly, we've included an interaction between this threshold and our continuous predictor of the amount of matrix habitat. And what this interaction term allows us to test then is whether the linear relationship between the effect of matrix habitat on woody species richness is constant, or whether that linear relationship differs below and above our defined threshold value. Okay, and in this case, from these biological data, That seems to be the case, where it looks like we have no relationship below the threshold. And once we get to this threshold of 62% matrix, then we start to get a decline in species richness with increasing matrix habitat. So in summary then, general linear models assume that all of our predictor variables influence our response variable in a linear way. Now, many biological effects are nonlinear, but luckily we can deal with these in a general linear model, either by transforming either the predictor or the response variable, or sometimes both, by using quadratic or polynomial terms to represent humped or squiggly relationships between a predictor and a response, or in some cases, using breakpoint regressions, where the relationship between some predictor and our response changes in a dramatic way below or above some hypothesized threshold. But in all of these cases where we're getting parameters for either our transformed predictor, our quadratic predictors, or our breakpoints, our interpretation of the linear models and the parameters that we get from those linear models always remains the same.